to start my talk, I chose this photograph I took 10 years ago because it has the three main elements of this story. Pebbles, lots of them, water, and a long journey. A long journey. This has been a long journey. So let me start from one of the early works that identified the fundamental role for the distribution and transport of water in the solar nebula. So here you see a cartoon from a paper in 1998 showing a section of the solar nebula. This is our sun. This is a spinning disk of gas and dust around the sun. And some key elements that we can see in this cartoon. First of all, a temperature structure that defines the chemistry and physics of this nebula and defines a region that many of you will have heard of, so-called the snow line. This region defines an outer colder region in the disk where water and this applies to any molecules, but here we are focusing on water. Water exists in the ice form and in the inner warmer region as vapor. Then there is a hotter, even closer region to the star, identified as being very chemically active. And on this side, we can see some fundamental dynamical processes. In particular, the drift of icy particles from the colder outer disk all the way to inside the snowline. So ice would sublimate. And vapor diffusion, become vapor, and vapor would diffuse outward. So in these early works, it was identified that, in particular, ice drift has a fundamental role in explaining some of the features of our solar system. In particular, observations of chemical gradients in meteorites, their oxygen content, isotopic ratios. And then to explain also the concentration of solid mass to speed up the formation of Jupiter. And thirdly, a time-dependent molecular gas content in the inner disk, favoring chemistry that varies with time. Now, all these predictions were so fundamental that they were later extended to protoplanetary disks in general, identifying a prediction where the outer region should be intimately linked to the chemistry of the inner disk through this large-scale drift of icy solids that would drift inside of the snowline, sublimate their ice, and then reach the inner disk with water. Now, this is a field of research that is extremely active today. So there is a growing number of works that are coming out and studying different aspects of it. But in this slide, let me highlight in particular from one recent work the fundamental time dependence of this process. So you see here in the left plot the inner disk water enrichment as a function of time, and to the right the pebbles, the mass of pebbles drifting inside of the snowline as a function of time. So let's focus on the dashed curve here. You see as the pebbles are drifting in, a larger mass of pebbles is drifting inside of the snowline. There is an enrichment in water vapor that reaches a peak around a few million years, and then followed by a decline. The decline is because there are no pebbles anymore, so the outer disk is being depleted. So there is not more the source of that ice, and also gas is accreted onto the star. So again, this is a recent version of a fundamental prediction for more than 20 years ago. Okay? Now, the role of pebble drift, though, goes a long way further than just this link between outer and inner disk. And in recent years, pebbles have been the intense focus of study as a key element in planet formation, in feeding planet formation. And in particular, in this slide, I want to highlight one aspect in this broader story of planet formation, the formation of super Earths, our bigger sisters, and the most typical outcome of planet formation. In particular, let me take this example from a recent work by Michael Lambrechts, where it has been shown that depending on the mass of pebbles that makes it from the outer disk to the inner disk and delivers solid mass to the inner disk, depending on the mass flux of that, the planets that can form in the inner disk could be systems of super Earths or rocky, smaller terrestrial planets. Here you see the mass of the planet. So you see this is Earth, right? So depending on the flux, this is the flux nominal, and this is 3 times that flux, the outcome of planet formation, the planetary system that would form in that disk is very different. Super Earths rather than little smaller than Earths. Now, this is one aspect of it, but now imagine if we were able to measure the mass of pebbles that makes it inside of 3AU. If we were able to do that, through these models, we could connect and be able to estimate and say which disks are forming super Earths and which are forming smaller rocky planets. Let's focus a little more this pebble drift. Pebbles. What are pebbles? Pebbles is a term that has been used more and more recently to identify a regime of aerodynamic gas coupling between solids and gas in disks. Okay? So pebbles are those solids that are not so small to be completely coupled to the gas and not so large to be completely uncoupled. They live in an intermediate region here where they are partially coupled, and so they feel this aerodynamic gas drag that would drift them in from the outer disk all the way to the inner disk. Okay? The size of the fastest drifters depends on where you are in the disk, because the density of the gas is also changing. So this goes from 1 meter solid objects at 1 AU to millimeter solid objects at 100 AU. This was recognized very early on in one of these fundamental papers where you can see the speed, the drift speed as a function of size of these particles. So now let's look at 1 meter solids at 1 AU. The drift speed is 0.02 AU per year. Multiply by 100, you get those meter solids all the way onto the star. What does that mean? The implications of this very efficient drift is no planets and no disks. There should be nothing, because this process is so efficient. And yet, we know planets exist. We see hundreds of disks. So there must be something in place that is making this process less efficient. So around 10 years ago, there was a group of researchers that tried to propose a solution. They said, okay, so let's imagine there is something in disks at large radii that is slowing down the process and trapping in pressure traps at least some of those pebbles, and keeping them outside in systems of rings. This was 2012, and I know you all know this is no prediction anymore. Since 2015, ALMA has stunned us with many, many images of these kind of structures in disks. This is the simulation. These are images from a very famous recent survey with ALMA. Rings, gaps, spirals, all these structures that indeed tell us that pebbles are retained in structures at these large radii. And I like also to highlight this other survey that was not biased only towards some of the brighter and larger disks, and showed us the full range of disk sizes, from the largest that always show gaps and rings, all the way to disks that are very small, only 10 to 20 AU in size. This is another field that is extremely active in these recent few years. Now you see these images come only from a few years ago, but already this wide range of structures and sizes has provided strong support to those predictions that were telling us, in order to slow down this drift, this so efficient drift of pebbles, there must be something in place at large radii that is retaining some pebbles outside there. Okay, and this is not happening. This is not the case for the smaller disks. But there is a caveat. And the caveat is, in this beautiful story so far, is that even at the maximum angular resolution of ALMA, now we are zooming in on the inner regions of one of these disks. This is the angular size of ALMA. We are essentially blind to the distribution and dynamics of pebbles inside of a few AU. So how can we test their fundamental role in planet formation, the formation of super Earths, if we are essentially blind to what happens to pebbles inside of a few AU in disks? By now, I hope that some of you will be wondering, hey, shouldn't this be a talk about JWST? Exactly here we go back to the story of water, the other half of the story. So can we see water in disks? And it was 2008 that researchers using the Spitzer Space Telescope made a great discovery. They saw that disks, we can observe a very dense forest of emission lines from disks, mostly from water, tracing warm water vapor inside of 1 AU in these disks. Now, this was the disk of A8 Tauri, which has been later imaged with ALMA as a system, a ringed system. And now I invite you again to recognize the difference between the spatial scales that we can see with ALMA and Spitzer. So here you see this is a 30 AU bar. This is the maximum resolution of ALMA. Here we are talking about water coming from the inner pixel, or a few pixels in this image, okay? Warm vapor inside of 1 AU. But now, even if we step for a moment back from these technical details, I think the most fundamental message of this discovery was that we can observe water at 1 AU in disks at the time of planet formation. So immediately, many of us, we couldn't avoid thinking that we could finally be able to learn more and from observations about the story of how water has been delivered to planets. Now, a story that is truly very dear to us here on Earth. But even here, there is a caveat. Let's focus this caveat here. So let's zoom in on a portion of this spectra in this other visualization here. You can better appreciate the density of structures, okay? In blue, these are emission lines from water. Let's focus even more on 3 of them. And now we can see the problem. So this is how we see these features in the Spitzer spectra. This is a model of water emission at the resolution of Spitzer. This is the same model at the resolution of JWST, and this is at even higher resolution. So now we see we have a challenge there. So in Spitzer, we are observing low pixel sampling blended features that contain multiple water lines. And why this is particularly critical, I will say in a couple of slides. But now, since I know that the concept of spectral resolution is less familiar to probably some of you, at least, so let me focus this better with comparing with something that is way more familiar to you. So again, this is a range of spectral resolutions, Spitzer and JWST. But essentially, what we are talking about is the same as the spatial or angular resolution in images. Now, so let me show you an example here. This is, believe it or not, it's the same disk, HL tau, as imaged with a different angular scale, 5 times better with now here in 2015. This was just 2011, so in just 4 years, 5 times better resolution. See how dramatic of an improvement this was. This just looks like a blob of stuff, and here, no, systems of rings, beautifully seen. And I like also this other example from folks at Space Telescope, showing how a far galaxy would be imaged differently in a low resolution, low pixel sampling situation, or high resolution. What dramatic of an improvement this is now in being able to resolve individual structures in the galaxy. All right, so bearing these limitations in mind, still Spitzer has provided us today with the largest treasure of water emission observed at the time of planet formation in protoplanetary disks. In more than 100 disks, we have seen and observed and studied and analyzed this type of spectra. You see a model of water emission in blue, and in black the Spitzer data, and here models for the other molecules that have been observed here. Now, a larger part of this sample of disks has recently been observed with ALMA, showing us for the first time that some of them are very large and with structures, and others are instead very small. So at this point, for the first time, we have the opportunity to combine these two data sets from Spitzer and ALMA for the first time to test those fundamental predictions from 20 years ago, about an intimate link between the dynamics of pebbles in the outer disk and the water enrichment in the inner disk. And what have we seen? We have seen this with Spitzer and ALMA, combining Spitzer and ALMA. This is the data, this is the interpretation. At the top here, you see 2 different versions of plots showing the correlation between the water luminosity as observed in Spitzer spectra as correlated with the disk radius as observed with ALMA. Now, these correlations show us that small disks have brighter water emission and large disks have fainter water emission. And this naturally fits into those predictions from 20 years ago. In fact, if you think about efficient drift of ice that brings pebbles, a lot of mass of ice inside the snow line, we should observe very large columns of water right there. And instead, if some of these pebbles are retained in system of rings, we should see a lower water emission in those disks. So, is this the end of the journey of the story? Not yet. Because so far with Spitzer, due to the low spectral resolution, all we can say is that small disks have brighter water, large disks have fainter water. But we cannot measure how much water is there. And here comes our hero. So what improvement do we expect? So here is again the same spectrum with the water model, and here is an illustration of the type of improvement that we expect to see with MIRI, JWST MIRI. So here you can appreciate more how not only we will be able to distinguish different molecular components that are blended, severely blended in this spectra here, you see all these structures, but also in particular for this story, we will be able to distinguish different water transitions blended in individual broader lines there, right? You see here, for instance. So, and why is this so important? So imagine you go for a walk in the morning and it's a very foggy morning, and all you see around you is mostly what you don't see. So we call this an optically thick situation. So your eyes are not able to see through the layer of fog, all right? So you can only see the surface layer of the fog on your line of sight, all right? Now imagine you could switch the wavelength of your eyes and instead be able to have different wavelengths to see through all the fog layer and count each individual molecule on the line of sight. This will be what JWST allows us to do. Again, an example here of how the increased spectral resolution will allow us to distinguish the strongest optically thick lines from the weaker optically thin lines. And here is a demonstration of the dependence of optically thick versus thin lines to a different column of fog in front of you, in this analogy, right? So the optically thick lines are saturated, they are not very sensitive. You can change the layer of fog, you can double it, you can make it 100 times larger, and you don't see any difference. And optically thin lines, instead, you can count all molecules on your line of sight. And so this brings us back to the full story, to the closing the circle of this program that was approved in cycle 1. So we will be targeting a sample of disks all the way from the smallest, seen with ALMA, 10 AU, all the way to the largest, 150 to 100 AU, that have rings that are retaining pebbles in the outer disk. JWST will, for the first time, distinguish optically thick, the strong lines here, from optically thin lines, and allow us to measure that column of water vapor, and with that, to connect it to the mass of icy pebbles that have drifted into the snow line, and therefore, through those models that I showed earlier, to the mass that is building super Earths versus rocky planets in that inner region. So, what should I say more than this? This should speak on its own, but let me end with a big thank you from all of us, in particular from the DISC community, for JWST. All of you who are connected here, and all who are not connected, but who are making JWST possible, and now coming up very, very soon. We are all very excited and very thankful to you all. Thank you.
All right. Thank you so much, Andrea, for an excellent talk. So we do have a question in the chat, and please write your questions if you think of some now. The question is, what size range of pebbles are measured by the ALMA images?
So in this story, I spoke about two elements, one that I'm more familiar with and one a little less. Right, the first part of the story is one that I have left and I rely on my colleagues on, but this is a question that I can try to address. So those ALMA images, if we go back to those, are mostly sensitive to only a range of solid sizes. We don't see, a little bit similarly really to this picture, we don't see the super small dust grains, we don't see the large bodies beyond 1 meter, actually beyond a few centimeters really, or decimeters. So really those ALMA images are mostly sensitive to emission from the drifters, from pebbles, as defined here, the millimeter, centimeter size images. Now there is a range of solid sizes that contributes to the emission, but so there are studies that try to define that from disk to disk, but we are most sensitive to this range of solids.
All right, thank you. Then there's some notes in the chat as well, just to remind folks what an AU is, an astronomical unit, which is the average distance between the Sun and the Earth. Thanks for that. And we also have a comment here that this is for the folks who are watching on Facebook. Another comment about that optical thickness is a measure of how much light is absorbed. Is there a way for you to distinguish between emission from in situ water and the water delivered via icy pebbles?
That's a great question. That's a great question, right? Because those disks should have, so those disks are naturally born gas rich, right? So they should have molecules throughout radii from the innermost region that is accreted onto the star out all the way to the outer regions, right? So there has been quite some work dedicated to trying to understand how to distinguish the two scenarios. And maybe we don't have a definite answer yet, but a signal now where the amount of water, or if we go back to we go forward, a signal where the amount of water that we see in inner disks is correlated to the size of that disk, is really telling us that there is some connection between the outer disk and the inner disk. And so that the fundamental prediction that is really hard to avoid, that those icy solids should drift in and go to the inner disk and sublimate at some point and so reach the inner disk, right? That story must be right to some extent, right? So in simple terms, what we could say is that situations where the column of water is low could be consistent both with a low drift of particles as well as with just the primordial gas from the formation gas from the formation of the disk. While if we see that there are way larger columns than what would be expected just from gas phase chemistry, and typical, if we can define those conditions for inner disks, would be more indicative of a source of that gas, of that vapor that comes from outside. But this is one of those subtleties in the story that will require a lot of creativity and skills from researchers, including Gaz and many others, not to figure out and fully solve.
All right, thanks. I think we have time for one more question here. How well constrained are the angles of these? I think it's inclination angles. Does your interpretation depend on the inclinations, and are there complications if we aren't sure of those angles?
Inclination angles of the disks? Yes. I would say broadly not. That's not one of the critical factors in this analysis. Now, the inclination, as now with the resolution of ALMA, now as people can see from these example images, is the definition and sensitivity show us pretty well the geometries of these disks. So inclinations from ALMA studies, disk inclinations have been proved a lot compared to 10 years ago. Now, so the inclination is not so much a critical factor as long as disks are reasonably face on in the sky. No, or actually, let me say the other way. As soon as a disk becomes really edge on, then we cannot see anything anymore. No, so we don't actually even see any water anymore, right? Because the disk is obscuring itself. And I know now those of you who are familiar with HST images of protoplanetary disk will immediately think of some of the earliest images that HST took of protoplanetary disk, where there are those beautiful silhouettes, dark silhouettes with brighter lobes on top and below, because that dark silhouette is the obscuration of dust in the plane of the disk of the light, right? So in that case, we don't even see the inner disk, but that's an extreme case, right? So it's really a limit, an extreme case of random geometries that you can see in the sky, right? So the largest population of disks at lower inclination, say lower than 70 degrees, all right? Between 0 is face on, and 70 degrees. In all this range of inclinations, we can see the inner disk, and so this story is applicable. Now we can study the inner disk water in connection to the distribution of pebbles.